Hey, everybody. All right, someone entertain us with a story to get us started. It's Friday. We need a like a farewell prologue. Lexi, tell me a story about the last time you were in a windstorm and a camel blew out of your grasp.
Driving home on the holidays, my sister and I were 10 minutes away from the shutdown, the grapevine shutdown, because it was snowing. So that was the closest to like a camel storm.
Camel
Crazy.
storm.
Like my sister would look back behind us and she's like, look, and like highway patrol just stopped everyone. We were like so lucky. As far as like a farewell story, I'm donating my hair today. So that's a good farewell.
Locks of Love or one of those things?
Yeah, or like children with hair loss.
Okay. Yeah, I think Locks of Love is like I think isn't that the little organization that collects it and gives it to, is Children with Hair Loss, is that another organization?
Yeah, so Locks of Love, they focus on like cancer patients, like little girls with cancer specifically, but I've always been hesitant with them because I heard that they sell your hair to the
On the
patient.
black market to
Yeah, so I'm like, you're
to
supposed to
runway
give it to them
models.
for free, but if you look at their website, they're like, oh no, if it doesn't qualify, we'll sell your hair as like a clip or extensions to offset the cost for cancer patients. So I'm like, I don't know if I believe you, but
Okay.
so yeah, one of the two.
Okay, good.
Yeah.
Are you going to come in with like a crew cut on Monday? How short are you going?
Probably 10 inches.
That's a lot of yardage. I'm tired.
So I'm like, yeah, I don't know if people will recognize me, but I can't go to here. That's just too.
Luckily on Zoom, it'll say your name at the bottom. So I think we'll be forced to recognize you, and you'll have a nice storm. Have camels in the background next time. You have a beach scene right now.
Will do. Or if my hair is just that bad, I'll just make sure you can't see me at all. That's how you know it's bad, you know?
The hat on, yeah. The kids will be very grateful. That's how tired I am. I forgot how to share a screen. Okay. So chat box is open. Same as always. Just say stuff if you feel like talking. Type stuff if you feel like typing. And we'll get going. We're gonna just talk about, we did overtraining, stresses of overactivity, overreaching, overtraining. We did physical inactivity, sedentary life, but somewhere related to overexertion, we do see injury and trauma, and you don't usually see trauma in the sedentary patient unless it's a car wreck or something. But in sports contexts and in athletic contexts, sometimes physical injury, trauma, these are, it's the 100-meter runner who pulls his or her hamstring. It's Ross's knee. It is, everyone's going to have something at some point. Some sort of, the harder you train, the harder you work, the more athletic you are, the more likely you are to endure kind of, macro trauma, and not just overreaching, overtraining, the summation of micro trauma, but actual macro trauma. And so that's what we'll talk about today. All of this stuff. And for the longest time, just know the names, including I guess Mario and Luigi, but for the longest time, Cellier was just the slogan of stress, and it doesn't really make sense in the context of this class to have Cellier be the slogan. Sort of everyone else is being a replacement slogan, sort of a surrogate slogan for what Cellier used to be. All of this stuff. And it's just all specificity of adaptation. The nature of stress, we're going to respond very precisely to tolerate and thrive despite the influx of stress, the abuse of stress. But sometimes you jump a little bit too hard on that trampoline and you tear some stuff. The trampoline gets a hole in it. One of the springs breaks, something like that. So there's sometimes you have all of these proteins, the cadherins and titin and integrins that are relaying messages about loads. And as long as those loads are tolerable, if those loads aren't so extreme that they cause uh, you know, irreparable damage, or at least damage that can be repaired in the long term, acutely irreparable damage, then we have other mechanisms for repair and regeneration, and we'll talk about some of that today. So over for today, it's too low, that's bad. Too little stress is bad. The little cuddly bear, whatever, that's too little. The big growling, bear with the fangs and stuff, that's too much. And that's what we're going to talk about today, is just too much stress. And it can happen in these contexts where it's just accumulation of micro trauma, right? It's not like one pitch does you in. You don't rip up your rotator cuff on one pitch, but the accumulation of those pitches, what you see is these catabolic signals predominating. Catabolic signals. It's all metabolic regulation. At some point, it's mostly metabolic regulation. But if you have this accumulation of micro trauma, micro insult, just little, to you, like nickel and dime, as the cliche goes, you nickel and dime your tissues to death, then it becomes a metabolic problem, and the dysfunction results from catabolic signals predominating over anabolic signals. But today, again, mostly what we're going to talk about is macro, not micro trauma. Micro trauma is more environmental stuff. Macro is a little bit bigger. So the fin snaps off, right? That's macro. This guy had recently had some macro trauma. That's unlikely to be the result of micro, where you put the cast on it. This guy looks like he's about to sustain macro trauma. He's going to herniate a disc or something. This guy's currently sustaining it. And we'll talk about the Achilles today. Of you go jogging, it looks like she's jogging maybe 5 miles an hour, 6 miles. That's not a huge um, stride that we're looking at. So we can look at how much of the load is being endured by her Achilles, and that's probably a pace that has an awful lot of stress on the Achilles. You can get 12 times your body weight and stress on the Achilles. It can usually tolerate it pretty well. Again, specificity of adaptation. And it gets so narrow, and just making sure you employ it correctly. Keep size principle in mind. Orderly recruitment, or size principle. Size principle uses the size of the motor nerve, the size of both the fibers, the motor unit, the motor nerve. All of that is bigger in the higher threshold motor units. Everything is bigger, and so that's what the size means. And again, we can have the same amount of stress is going to hit people differently. You step off a curb, for one person that snaps their Achilles, for another person, your body doesn't even notice. You're asleep. You're sleepwalking. Literally, you can be sleepwalking doing it. Another person, their Achilles rolls up into the back of their knee. So we have to be able to stratify people according to risk. And this is just big picture. This is huge picture risk, is the PAR-Q. Should you do anything at all, or should you go home and go to bed? Right? That's PAR-Q. And we use that for a 2-minute exclusionary criterion of some criteria. I guess there's 7 of these things, but that's just to rule out people on huge picture stuff. Big picture is more ACSM. Are you going to have, are we up against sudden cardiac death stuff? And it's really helpful to do, but it doesn't really tell you if somebody's at risk of an Achilles rupture, if somebody's at risk of rotator cuff problem, some sort of tendinopathy, what people used to call tendinitis, some sort of pathy, where you're having a problem with the tendons. And you know what overreaching and overtraining look like. We're looking at the hypothalamic and go from there. Axes, hypothalamic, pituitary, whatever. Axes. Let's give Selye a little bit of credit. Yeah, he was a slogan of stress in an inappropriate way for an awfully long time. But in the 1930s, he did have some really good ideas. And focusing on this, when we're talking about overtraining today, we're really talking about what did Selye say about stress? And that gets into sort of overtraining and the summation of stresses. There was something true about what he was saying. You can't just throw it all away. I like to throw it all away and make fun of it because I'm so adamant about specificity in my lectures. Specificity of adaptation is one of my go-to topics. And so Selye is sort of the enemy of that, but a lot of what he said actually was sound, and he isn't a total buffoon. He was a smart guy. But again, I like Edward Adolph much better because specificity of adaptation. This is not Selye. Now, you just remember the Whitehall studies that these things are talking about. There's more to the picture. There's always more to the picture. Don't be too bold. Don't be too sure. Don't dig your heels in. You should wear bowling shoes. You shouldn't wear cleats in terms of your emotional attachment to things. You should be movable. If somebody presents a good argument, that should kind of move you. You shouldn't be dug in too deeply. Smoking and sitting, that cliche. The idea of not squatting is a major input for stresses, and just looking at these muscles that connect. That if we're in the lumbar spine and pelvic muscles, really this is the core of everything, of athleticism and human function and reproduction. And everything is here. And so sit all day and you're just going to mess everything up. Sit all day and you go through the alphabet with diseases. And this is just one example, that LPP1. And we do, find, okay, you're a tennis player. Do you play tennis as much as you sit? Probably not, right? How much time do you spend on the court, doing drills and competing? And probably less time than you spend sitting. And that's that way for most sports. Basketball players, they probably sit more than they play basketball. They're way better at sitting than they are playing basketball. World class at sitting, and maybe they're world class at basketball. Let's hear LeBron James. Yeah, you're actually better at sitting than you are at basketball, but you are really good at basketball too, right? Basketball may be the thing you're second best at in life, and he's supposed to be a really good sleeper. So maybe sleeping is the thing he does best, sitting is the thing he does second best, and basketball is the thing he does third best, and he's world class at that. So we're all sort of world class sitters because we do it so much. Now, what does that mean? Our posture adapts. Our posture, we become the embodiment of whatever postures we endure. And so what muscles are shortening, what muscles are lengthening, and again, over here at the distal end, the hamstrings are being shortened, and at the proximal end, you're going to see it's a two joint muscle. So you might see a slight difference from end to end at what they're doing. And that concept of food and abundance, we should connect the two. We should connect food and activity. And later in the semester, at some point, I don't remember exactly where it is in the syllabus, but at some point this semester, we're going to talk about fasting. We're going to talk about starvation, and we're going to talk about fasting. And fasting from the perspective of you're doing this on purpose. There's a beginning, a middle, and an end. It's well controlled. There's a duration. There's water involved. There's a healthful approach to this, and starvation. You can think of that as this uncontrolled, involuntary, spiraling toward the grave version of fasting. Fasting is a deliberate version of starvation that's you begin and you end in this healthful zone. We're going to talk about that. And that is a little bit of an exception to this concept of food and abundance and movement and connecting movement to food in the ingestion. We'll get there. But for now, we use exercise and we use physical activity. We prescribe it to ward off the effects of what we just overate. Right? Oh, I shouldn't have eaten. So I go to a buffet. That's the worst thing in the world. I can't go to a buffet because I need to beat the house. It's, oh, it was $20 or whatever. I need to eat more than $20. You keep all the cheap food over there, and I'm going to eat the bad seafood for $80 worth of bad seafood. And I hate myself when I'm over. It's just like self-loathing when I'm done, and I've destroyed a belt. I didn't even like undo the belt. I've cut it off and thrown it in the trash because it was a loop of discouragement. And that's what we do when we go to buffets. And then like, oh, what do I have to do? I should go get on the elliptical. Like, well, that's not. I mean, we are forcing these puzzle pieces together. It should be a little bit more natural than that. We should be able to connect movement and food in a little bit more natural of a way where it's not just, you know, Lord, forgive me from I have sinned. And you start using the elliptical or the treadmill or going for a walk around the neighborhood or something. And Ansel Keys know this study, the Minnesota starvation experiment, where he's using these the conscientious objectors, World War II, draft dodgers, essentially, who they volunteered for this study, but the starvation study, and you give them some rutabagas and a little bit of macaroni and some turnips and potatoes, right? So you give them these things, but you control the amount. You control a small amount of these things, and make them walk a bunch. And what happens when they're doing this? Remember, early on, and you can induce this with fasting. It's not starvation, but starvation would be a similar phenomenon early on in starvation, or for the duration of fasting, provided you do it for what we would consider a healthful duration. You'll see an increase in focus, an increase in this frenetic surge, right? So you look like I don't know, frenetic. Think like a chipmunk or a squirrel running around, jumping around on a tree, sort of fast, darty movements, and hyper alert and vigilant, and your attention is enhanced. And that sort of sensation and movement characteristics accompany you early on, and then you crash, and then you're lying in bed for 20 hours a day. You become a cat. So you begin fasting or starvation as a squirrel, and then you evolve into a cat in relatively short time. Now, all of these movements that we have, in youth, as we begin young, we begin, little tiny kids, and we're moving or dancing or shaking a hairbrush or I don't having a seizure or whatever this is. All of these movements are informing us. They're informing us how we can look back on what just happened. All right, this motor action, here's what happened at the macro level. Okay, let me remember that one. So if I need to do that again, I know how to voluntarily execute that task. None of this stuff is worthless. We're paying attention to what we're doing. But if you want to heal, if you want to get good at sports, if you want your tissues to regenerate, you can't cage it. Right? You can't put it in a cast. Now, short term, yeah, you have like your bone is sticking out and whatever. Okay, you cast it up, clean it up and make sure that bones are articulating. If you have bones that are just not even touching, that's in muscle physiology, I talk about tissue healing, and you got to have bones touching. Right? If your bones are like pointing in the wrong direction and stuff, that's never going to heal. So let's get your bones set, and let's get all this tissue articulation and cast it up for a little while, because there's a tiny amount of loading is just going to re-destroy it at that point. Think about tissue paper, toilet paper. Think about toilet paper, right? Just like it has a little bit of integrity when you pull on the ends of toilet paper, but if it's a little bit damaged and you pull on it, it just rips in half immediately. And what you want is like 3-ply toilet paper with no micro tears in it, and that stuff will have. So that's not going to like rip apart as you're trying to wipe your asshole. Let's make this PG, whatever. So put a cast on for a little while, and once the tissues are healed enough, now you need mechanical signaling. Now you need mechanical signaling for that. Now just remember that we sit a lot. We sit, and that's not good. If we get stressed out, the bear is roaring at you, and we're having this hypothalamic pituitary adrenal axis and the sympathoadrenal medullary axes, these things. If we're having these and you sit down and take your test or something, that's not helpful. That's not helpful. And one of the major differences in people who have higher BMIs and people who have lower BMIs. Remember James Levine, I talked about him in the last lecture, is non-exercise activity thermogenesis. Neat, right? Non-exercise activity thermogenesis. One of the major differences is how much NEAT do you get? What does your Fitbit say at the end of the day? Did you get 9 out of 9 active hours? Did that little vibration happen? Did you get the 10,000 vibration? Did you put it to 20,000 and that's your vibration? Did you participate in pickleball and pickup basketball and whatever? What did your day look like? Is it a bunch of non-exercise activity thermogenesis, or is it just, oh, I jogged for 20 minutes and I did 30 minutes of weightlifting, and then I was prone and supine. I toggled back and forth between those two postures for the rest of the 23 hours and change. So NEAT, hugely important. And if you just compare these things to basal metabolism is 1, right? So this is a MET value, metabolic equivalent of the task, MET, MET. And the MET value of 3.5 means you're 3.5 times your basal metabolic rate. You're burning calories, consuming oxygen, right? You are your metabolism, you're consuming energy substrates at an accelerated rate, 3.5 fold accelerated rate. So you just stand, get walking, and it's going to go up even more. Be a little bit, extra ambulatory in your walking, get a little bit more intense. And we're seeing this increase in the metabolic equivalence of the task. So just be physically active. And remember your skeletal muscle, how this behaves. That if your skeletal muscle wants nutrition, we're going to talk a little bit about this today. We're going to talk about the vasodilation piece today very shortly. We'll get into vasodilation and reactive hyperemia. What pump, you go to the gym and you exercise and you get the pump, right? This hyperemia, we'll talk about that. But the right here, reactive hyperemia, whenever you see that, that's like you're doing bicep curls and your biceps get huge and then you try to show off before it goes away in 20 minutes. But so the skeletal muscle pump, this isn't the gym pump, this isn't hyperemia, this is your calves and your glutes and quads, and so this is blood is pooling in your lower quadrant, and gravity is pulling down on all that 5 liters of fluid inside of you, and of blood, the 5 liters of blood inside of you. You have a lot more fluid than that. So the blood is being pulled in the direction of gravity, and the blood pressure is not high enough to overcome gravity. So what do you need to do? Flex muscle. Use your muscle, and the flexion of that muscle puts mechanical pressure against the vasculature, and that squeezes, just like a toothpaste tube, it squeezes it, and it only goes in one direction because there's valves that prevent backflow. So it only goes in one direction, so the blood has to go in the direction of the heart. So use skeletal muscle and you're returning more blood flow to the heart. GLUT4 density and GLUT4 translocation. AMPK, this is better than insulin. Insulin is the at-rest thing. Insulin is your muscle sort of not picking up after itself, your muscle making a mess, or you're eating, I guess, making a mess, and then the muscle not being a good, I don't know, house guest or a good the muscle does not clean it up. If you're just lying there taking a nap and you're just accumulating a mess, right? Insulin is going to come through and pick it up, but it's gonna like break your shit at the same time. Like, okay, here's a good example. I have yard people, like folks who come to the house who do, they like mow the yard and clip bushes and whatever. And anytime I leave something outside, they break it. I had these glass candle things outside. They're all shattered. Every time I leave plants outside, they come through with that like leaf blower thing. They can't just use a damn rake, right? They have to come through with like a leaf blower and just tip over every single flower pot that's in the backyard. I mean, they just like break all my shit every single time they come. I like having them, but I'm like, oh, what are they going to break today? And I actually watch them. It's like a voyeur activity. What are they going to break? And I get excited to see what they're going to destroy of mine. That's insulin. Insulin is going to come pick up the problem that you're not cleaning up, that the muscle isn't cleaning up, but it's going to break your shit at the same time. It's just going to leave a mess, and you're going to get insulin sensitivity problems, and you're going to have to pay for this later in life with illness. And if you just use muscle, you're going to activate AMPK. AMPK is going to increase the amount of GLUT4 you have. Right, it's going to increase the GLUT4 content. It's going to translocate GLUT4 acutely. You're going to call sugar into the cell. It's going to consume it. It's going to activate hexokinase, right, to use glucose. Hexokinase is the first step in glycolysis. If you're using glucose, when you're using glycogen, you totally skip hexokinase. But PFK, phosphofructokinase, that would be the third step in. I just did like the quotation mark with 3. Let's just say that's the third in quotes. And so the third step, if you begin with hexokinase, is going to activate that too. And so let's consume all the glucose we're getting in. So muscle, wonderful at picking up any messes. And then it has to get the blood to it. So downstream from the skeletal muscle pump, let's change the diameter of our blood vessels and send blood to where it's needed. You need to use muscle. You have to use your muscle for that to happen. If you're not using your muscle, you are not getting these vasoactive molecules that are going to control the dilation, how constricted, how dilated the blood vessels are. So muscle earns its calories, earns the blood that's going to it, earns the sugar that's going inside of it. Now, when muscle's inactive, remember, it just starts going away quickly. So muscle is inactive, and that vanishes faster than we all think, faster than we'd like. And so that's why we see things like sarcopenia being a problem in older adults who get a little bit more sedentary. Life gets in the way. Maybe they have kids. They have, a career that's really demanding. They can't get out of the chair. They're in the office all day long, and then suddenly they've lost 25 pounds of muscle. It really goes quickly. Muscle goes quickly. You have to show your body that this is something you want to keep. And I'll talk about that a little bit later as we get into things like MyoD. I'll talk about later. And just a bunch of studies talking about the percent of loss per day, the daily loss of muscle in these mostly kind of bedridden studies. And so we're just not burning the calories that we think we are. We're not burning the calories that we think we need. And certainly we're not burning the calories that we actually need. Okay, that's our review over. Moving forward, functional hyperemia, reactive hyperemia. Think of an acute. This is temporary. We've all gone to the gym, and you're not going to get it lifting pink dumbbells, but you go to the gym and you get a pump. It's like, oh, my muscles feel like my skin is stretched, my muscles feel full, right? So that's an acute exertional increase in blood flow, and it's not everywhere. Go work your biceps. You don't get a pump in your glutes. Right? Go work your glutes. You don't get a pump in your biceps, right? It's a very localized. Now, it's not so precisely localized. And I'll tell you why in just a minute, the mechanism. I'll tell you how in just a minute, but it's muscle group localized. And so it's the perfusion. We have this ischemia perfusion exchange where if you put a lot of the research on this is put a blood pressure cuff on, right? Inflate that thing, inflate a cuff and occlude blood flow temporarily, right? Temporarily occlude blood flow. Now here we're looking at 5 minutes of ischemia, and then you release that cuff and watch what happens. What happens is here's rest, ischemia, reactive hyperemia, where we have this compensatory increase in blood flow, in kind of red blood cell content pouring into the area. And so that's what hyperemia is. Go exercise, and in part, in exercise, you're occluding the blood flow. In part, there's a lot more to the sort of meathead, kind of bicep curl hyperemia than occluded blood flow, but that's part of it because you're getting this back and forth flex, relax, flex, relax, and whether it's a whole set of flexion and then relaxation between, or rep by rep, you get to the top of the bicep curl and then relaxes for a second until the gravity hits the weight again. And so there's intermittent sort of intervals of relaxation in a single set, as well as between sets. And so you do get this occlusion of blood flow. You get an ischemia reperfusion response, but there's a lot of metabolites that are going to be involved in this. Go exercise, you're going to occlude the blood flow and get the same thing, but go to the gym and you're going to see a lot of these byproducts of exercise causing this. These byproducts of exercise are going to be causing this. And prostaglandins, what that is, it's arachidonic acid, right? It lives in the sarcolemma. It lives in the phospholipid bilayer, and you go to the gym, and especially eccentric or eccentric loading, do a bunch of that, and you'll get PLA2, phospholipase A2. It's an enzyme, it's an ACE lipase. It is liberating this arachidonic acid from that phospholipid bilayer, and then cyclooxygenase, COX, cyclooxygenase converts it into prostaglandins. So prostaglandins is one of these things. Potassium being leaked, probably, right? When you see potassium being leaked, that's probably contributing to the vasodilatory response. Lactate, you're going to generate a bunch of lactate, use high threshold motor units, or if you put a cuff around, if you put a cuff and inflate it, well, you're not getting as much oxygen. When you're not getting as much oxygen, what do? More anaerobic metabolism, less oxidative metabolism. What is a byproduct of additional anaerobic metabolism? More lactate, right? More lactate. You're going to get more hydrogen ions if you're using, especially if you're using type 2 higher threshold motor units. You're going to be getting a lot more hydrogen ions. And so those also are going to be contributing. ATP, ADP, these things are going to be contributing. Adenosine, with or without the phosphates. Adenosine is going to be one of these contributors to hyperemia, so adenine and a ribose, but ATP, stuff like that is going to contribute. Maybe bradykinin. Bradykinins, maybe it's a protein that might contribute. The contraction by itself, the muscle contraction on its own, is likely contributing. You're getting this compression and then an opening, and compression and an opening. There's mechanical stimulus there, and so a lot of things are going to contribute to the perfusion, like if the ischemia and then the reperfusion, but the hyperemia, how much blood flow is going to go, how much vasodilation are we going to get? What are those vasodilatory agents? There's a lot of things. Now, there may be muscle fiber type explanation. Think about type 1 versus type 2 muscle fibers. Type 1 muscle fibers, very oxidative, much more efficient in their metabolism. They're less hydrogen ion accumulation, less lactate. You're going to get less of these contributors in a type 1 muscle. In a type 2 motor unit, a type 2 in a single muscle group, let's say it's abs, yeah, it's mostly type 1, but there's some type 2 in there. Every single muscle, you're going to have some type 1 and type 2. Every skeletal muscle, you're going to have type 1 and type 2. But whatever the skeletal muscle, if you're using some type 2 muscle fibers in there, if you're lifting something a little bit heavier, you're likely to get the metabolites are likely to contribute more to this hyperemia, functional hyperemia, reactive hyperemia, exertional hyperemia, whatever you want to call this thing. The muscle groups, the fiber types. Now, muscle groups, think gastroc versus soleus. Soleus is a bunch of type 1, mostly. There's type 2 in there. Gastroc's a bunch of type 2. Mostly there's some type 1 in there. And so the gastroc is more likely to contribute to hyperemia than the soleus would. So muscle groups, but within a muscle group, there's also the nature of the load that you are heaving, the nature of the load upon the tissue. And now this isn't just skeletal muscle. When you're looking at hyperemia, we talk about skeletal muscle because I do muscle physiology. That's my topic. But yeah, I mean, you just look at any organ, going to the liver, going to the kidney, going to the intestines, the skin, where you're going to see the same thing. Where if you occlude blood flow, you're going to have this reactive response, hyperemia, a reaction of occlusion and then perfusion, excess perfusion, wherever you are in the body. You're going to see this same thing, and it can be a problem in a lot of areas. Skeletal muscle, who cares? Whatever, it's fine. You just get a big pump and whatever, you're fine. Now, also the nature of the load, right? We've been talking about this all semester. The nature of the load, the nature of the stress or the load applied to a tissue determines the response. Yeah, Cellier, that alarm reaction, right? That immediate, that acute alarm reaction is generalized. Mostly when we're looking at hormones, things like that. But even this is very acute. This is duration in seconds of an occlusion, and then what happens after that, right? Do you occlude for 60 seconds, 90 seconds, 2 minutes? Do you go for 3 minutes? Yeah, how long are you holding this occlusion, and then what happens with the red blood cell velocity excess? What happens after that? So it depends on the nature of the load. It depends on the tissue. It depends on the nature of the load. Are you using high threshold motor units? Is it just occlusion? What muscle group are you in? How long is the occlusion? Remember, the fingerprint of a stress, the fingerprint of a load that a tissue withstands, that is applied to a tissue, determines the precise characteristics of the response, and the body's going to do its best to respond appropriately, ideally, to that particular stress. Now, sometimes it's not good. Sometimes the response is we get these like reperfusion injuries. So sometimes it's not ideal. But think about specificity in all of this, in the pump, in the skeletal muscle pump, not like if you open up a physiology textbook and see skeletal muscle pump, right? They're talking about valves, venous valves in your veins because the blood pressure is so low that it doesn't move. That's a skeletal muscle pump. But the pump, the bro science pump, is hyperemia. And what tissue are you in? That matters. Is it the muscles, the kidney, right? What is the stimulus like? Is it a high load? Is it a long duration? Is it dynamic? Is it isometric? Is it exercising during occlusion? This can trigger mTOR, right? Exercise during blood flow occlusion. This, with a lower weight, you can stimulate muscle growth as though you're lifting a heavier weight. So there's ways to employ these sorts of things, but the intensity, the volume, the climate that you're doing this in, all of this matters in terms of your body's response. How does your body determine blood flow into a tissue? Depends on the stress, depends on the load, depends on the nature of the stress combined with the load. What is the profile of stresses? What does all this look like? Now, the biggest difference in where blood goes, the muscle. Let's talk muscle. This sky blue color over here, the sort of summer sky blue color. This is muscle. And from this article, and it is here's muscle at rest. How many liters is being sent around here? Wow, a lot of liters of blood flow during maximal exercise in a non-athlete. 20 liters a minute you're sending through systemic circulation, and 40 liters a minute in an athlete. You can send a lot of blood flow. Total cardiac output huge in an athlete. Huge in an athlete. Less, but that's actually pretty huge too, in a non-athlete. But the big determinant of where all this stuff is going, just vasodilation. I mean, that is all changes of every other metric, right? Every other parameter, cardiovascular parameter, vasodilation. That's going to be the big one. Now, how do we control vasodilation? Well, metabolism. Metabolism is what determines vasodilation. So think about advice people give, or cliches, or conventional wisdom that people harbor. Oh, you go to the massage therapist, and I'm giving you a rub down. What am I doing? I'm increasing circulation to your tissues. That's what they say. Now, is that true? Sure. Yeah, fine. Yeah, okay. It's increasing circulation a little bit. Yeah, a lot. Nah, not unless you're flexing in response to the. If they rub you, let's say they, I mean a masseuse named they. It's a woman. They is a she. You go to they's clinic, and she is rubbing your calves or your back or whatever, and they tells you in a very calm, almost whispery, not quite seductive because that might be creepy, but a very calming tone. I am increasing, and she has a very masculine voice. I am increasing circulation in your low back and in your calves, and whatever that's going to help the healing process, whatever it is. I'm escorting toxins out of your tissue, or something like that. That's what they're going to say. Now, what determines blood flow? It's metabolism. Okay, if it's one of those like Swedish deep tissues and you're flexing against it because it hurts so badly, sure, you're increasing blood flow. What is the driver of blood flow? Your flexion, not the pressure on it. Is that going to increase blood flow? Again, maybe, sure, a little bit, fine. Yeah, not a lot though. Not like on that earlier slide where it shows this giant amount of blood flow going to the tissues. Metabolism drives that. Metabolism drives blood flow. So while you're getting a massage, what is the what tissue is receiving the most blood flow out of the two bodies there, out of you and they? What tissue is experiencing the greatest influx of blood? The masseuse's hands, forearms, whatever tissues they is using to massage you. That's where the blood is going because of metabolic demand. Metabolism drives blood flow. And remember the compendium. This is Barbara Ainsworth's compendium, and I'm sure a new one is coming out any day now, unless just came out and I missed it or something. But depending on your activity, are you doing carpentry, installing rain gutters? Maybe 6 times your resting metabolism. Are you lying down on a massage table as they Swedish deep tissues you? Nah, it's not going to be 6. That's not going to be 6. Right? Why would you get the blood flow to support 6 if you're not using 6? Is it that axe chopping? Is it a steel mill vigorous effort? What is it that you're doing that determines blood flow? Now, what is the mechanism that your tissues use to relay the need? This is interesting because what is the vasculature that offers oxygen, that runs blood through the muscle fibers? Well, it's capillary beds. Do capillary beds change in their diameter? Do you vasodilate and vasoconstrict capillaries? No, they don't have smooth muscle. So you're not determining where the blood goes at the level of the capillary bed. You're determining where the blood goes upstream from the capillary beds. So you have to go into the arterioles. You have to get some roadway behind, some upstream roadway that feeds into the capillary beds. That's what determines where the blood is going. Now, interestingly, a muscle fiber is a cell, right? And these cells are big. One muscle cell is gonna have multiple capillary suppliers for its oxygen supply. It's going to have multiple capillaries, and those capillaries probably aren't even coming from the same upstream arterial, right? So when we are dilating and constricting to send blood to a skeletal muscle fiber, to a cell, we're dilating multiple arterioles. Now, if you look at skeletal muscle and individual fibers, one motor unit is sort of shotgun blasted in where those fibers reside in that fascicle, right? So it's they're not a bunch of neighbors. It's not a cul-de-sac where it's a bunch of houses right in a row. That's what one motor nerve activates. One motor nerve is like a house in your neighborhood and a house in the next neighborhood and a house two streets over and it's a house down the street from you and maybe one of your neighbors, but then a house on the next block. It's scattered around, and so in each of these muscle fibers is has likely multiple capillary suppliers, and so you're going to have to dilate a lot of upstream capillary beds, and so you're not dilating this stuff, these capillaries. It's the upstream arterioles that you are dilating, and some of these you might have multiple of these guys. These little, the 4A over here, multiple of those supplying a single muscle fiber. So we're going to get a pretty good pump in the weight room. Long-winded way of saying we're going to get a pretty good pump, and we know what's going to do it, right? We know what's going to do it. We have all those metabolites, those vasoactive molecules that are going to inform the circulatory system, cardiovascular, circulatory system, that more blood is needed. Hey, I'm working out hard here. I'm doing biceps. I got some isometric stuff going. I am doing some heavy things. I'm cheating it up and doing heavy eccentrics on the way down. That's how you're really going to get a pump. And generating a bunch of hydrogen ions and a bunch of lactate, two totally different things, right? And maybe some potassium maybe leaking out. There's some prostaglandins here. Red blood cells can release ATP when pH and O2 get low. When both of those things start to get low, so it becomes acidic and oxygen is low, the red blood cells themselves are releasing some ATP. And all of these things, this collection of these vasodilatory byproducts of these agents, is going to be the information, the telegram that informs the circulatory system that diameter needs to increase here, right? We need more. It's like FedEx at Christmas, UPS at Christmas. We need some more trucks coming through here, right? The amount of the labor here is excessive. We need more employees. We need more resources. Let's at least feed our employees. So that's how hyperemia works. Nice little article here that talks, this is probably the best article on hyperemia. It talks about a lot of the things that can contribute to this stuff, and how the capillaries are their proximity to the skeletal muscle is a great, it positions them for diffusion, but the dilation and constriction is upstream from those capillaries. So why is this stuff, why, how, really, what I mean is how is this stuff swollen? Like, they go to this is the era of bodybuilding that I know, is Jay Cutler and Ronnie Coleman and Ronnie Coleman and Ronnie Coleman and Ronnie Coleman. So they go to the weight room, they go backstage and pump up, and we know how their muscles get super pumped up. Now, maybe they're having issues with their kidneys too. They're eating a ton of protein, and all right, so maybe we're having some kidney issues. Okay, fine. There's hyperemia all over the place. Ischemia, reperfusion, and so we get all. But how does this stuff get swollen? We know the mechanism of that, but how does this stuff get swollen, right? So we get injured. Let's say Ronnie Coleman is squatting and he tears a muscle. He's running and he tears a muscle. He probably would, because that body's not equipped for running. He's doing bicep curls and he tears something, right? He gets some strain somewhere. It's probably at the myotendinous junction. I'll talk about that in a minute. But the swelling here, this is different. This isn't like hyperemia. Now, what happens here? You get an injury. I don't care what the injury is. All injuries look kind of the same. We can almost celiate these injuries and say general healing response to a degree. There are magnitudes of healing that are very different. The chronic healing is remarkably different. The acute healing is similar. This is sort of a celiate thing where this general alarm reaction, we do see a similar function in the healing of a tissue, no matter what it is, right? A knife wound, or you stub your toe. Let's say that you stub all of your toes all at once, or you close your finger in a door, or whatever the hell's happening to this finger, or Ronnie Coleman, tears a bicep or something. This stuff gets swollen because it gets leaky. The vasculature is going to get leaky, where you get an injury, and then immediately upon an injury, what happens is you vasoconstrict, right? Because you disrupt a bunch of blood vessels and lymphatic vessels. You disrupt vasculature and you start leaking, and that's bad. You don't want to just leak forever. So you actually vasoconstrict acutely, and then you clot, and you plug up that wound, and then you get uh, the resident macrophages and the platelets. The platelets adhere to that clot, and this fibronectin and fibrin, and this little cross-linking, and the platelets come up and adhere to that, and there's resident macrophages. They send out these signals, these chemotactic signals, to say, all right, let's bring in the goods. Let's bring in a bunch of cells, immune cells and some proteins and all the resources and troops to start fixing this stuff. And then what happens is the injury is outside of the tissue. Swelling, yes, Kendall. Yeah, these pressure, wherever the proteins go, water's going to follow. If proteins leak out of vasculature, water's going to follow. And so we get all this vascular leakiness. It's prostaglandins cause it, serotonin causes it, platelet activating factor and complement proteins, and I mean, tons of stuff is going to make it leaky. And then it leaks out because you have to get these cells, these immune cells, you have to actually get them into the tissue so that tissue can heal. The tissue isn't going to heal. The injury isn't inside. If Ronnie Coleman tears his bicep doesn't live inside of his blood vessels, right? His bicep isn't entirely contained within his vasculature. And so you send all of these, immune cells and proteins, and they're not going to get to his bicep unless they actually get out of the vasculature. That's where the bicep lives. And so the vasculature gets leaky, and then all that stuff escapes the blood vessels to get to the site of the injury to clean it and whatever. And at that point, wherever these proteins go, water's going to follow. And so water follows, and then you get swelling. So swelling and inflammation, never confuse those two things. Swelling follows inflammation. In no way are they even close to the same thing. Swelling and inflammation have nothing in common but their sequence. Inflammation comes first, causes vascular leakiness, and proteins leak out of the blood vessels, and where proteins go, water follows. Now, let's say this is a skeletal muscle injury, right? So we're having loads placed on our tissue, loads and stresses placed on our tissue. And this is earlier when I said that lady was running, and let's say she's running 5 miles an hour, 6 miles an hour. It didn't look like she was sprinting. It didn't look like she was walking. She's running and sort of in a jogging position, and there's a big foot strike in that. You watch somebody jog at 5, instead of that awkward space, 4 miles an hour, 5 miles an hour, 6 miles an hour, and there's a lot of vertical displacement in these people. It looks sort of silly. You can either walk super fast or you can jog super awkwardly. Get into that position, and you're looking at the tendon forces, and you're measuring up to 12.5 times the body weight the Achilles is enduring. 12.5 times the body weight that the Achilles tendon is enduring. It can handle a lot. Earlier in this semester, I'm sure I've talked about the Achilles of needing great stresses, right? You're going to need, it's okay. It's easy to cut through the thing with a chainsaw, right? It's Texas Chainsaw Massacre. Sure, your Achilles is gone in a hurry, and so is the bone. A turkey knife, you're going to cut through the turkey, like the 70-year-old guy who proudly cuts the giant turkey on Thanksgiving and is standing at the dinner table with so proudly with the turkey knife. Okay, yeah, you'll get through the Achilles eventually. Butter knife, you're going to take a lot of carving with a butter knife to get through that thing. I mean, it's 12.5 times the body weight. So why does a tendon rupture then? Why do we see all of these Achilles ruptures? We'll get there, right? But what we see is length changes, resting length, and over here 5% increase on this resting tendon length, and with the strain on the tendon and how much can it endure. So think about somebody who is wearing a shirt that's maybe a little bit too small for them and it has buttons. So like, they're wearing a childhood shirt and they just love it. It's like their blankie from when they were a kid, but it's a shirt version of it and it has buttons and they're still putting the thing on. And they just, I had a shirt that I loved, and I wasn't supposed to put it through the dryer, and I accidentally did, and it came out a tiny person's, like a little child's shirt, and I still have it because the shirt was like $200. And it was this like hand knitted from like purchased in Italy and given to me as a gift. Sure. And if I, I put it on once and I had to immediately take it off because the buttons were just barely hanging on. It was about to rip. It was about to rip. And how much strain, how much stretching can that fabric endure? There's a point where the buttons would just rip open, the fabric would tear, the buttons would go shooting off. And at some point, I'm going to give it to a tiny person. I plan on giving that shirt to a tiny person. Say, no, no, no. It says don't put in the dryer, but have at it. It's shrunken as it gets. But think of your tendons in that same way, right? They have been shrunken in the dryer, and they just, all you have to do is put the length at 8%, 9%, 10%, and in that range, you're going to see rupture, and you're going to see different amounts of strain depending for that tendon, different amounts of strain for different loads. And again, tendons can handle quite a bit, but they can't handle too much. And over time, if you have inappropriate mechanical loads, over time, they can handle less and less and less and less and less and less. If you have healthy mechanical loads, they can handle more and more and more and more and more and more. A tendon might be 70 or 80% of its dry weight, not like how much wetness is in there, how much water is in there, but of its dry weight. A tendon might be 70 to 80% collagen 1, thick, nice, healthy, structurally sound bands, linear bands of collagen. And that's where that tensile strength comes from. That's where you get this elasticity and the stiffness and the recoil and that is that integrity. It's a bunch of collagen 1. Now over time you can degrade this thing. Over time that tendon can become a little bit garbagey, and that's when you're going to start to see these ruptures where it doesn't take 12 and a half times your body weight for the tendon to be okay still, right? It just takes stepping off one curb, and then you're screaming in the middle of the road, and people are uncomfortable. People actually aren't uncomfortable. They're just so eager to film you and put it on YouTube because we're such a horrible species. And so then now you're like a viral video on YouTube by strangers who took an iPhone video of you with like your tendon rolled up in the back of your leg. And that's what's going to happen. And why does that happen? Load profiles. We have these terrible load profiles. So remember this thing. Remember our little bell curve right here. We need to have nice loading. If you have too low of a load, we're degrading our tendons. Right? Our tendons are degrading. Too high of a load, bad. That's also bad. It's Goldilocks. Our tendons need to be Goldilocks for a really long time. And long term, too much or too little loading is going to elicit a disorganized response, a response that does not maintain, does not preserve the architecture that is the healthy architecture that you would like. And so you're going to get up to 8%, 9%, maybe somewhere around there, certainly 10% strain, and you're going to get failure of the tendon. Now down here, you might get some micro trauma where it's just hey, every day you're doing this thing and you're not giving yourself a break, and you're spiraling toward overtraining. Every day you're just coasting in the direction of overtraining. It's just a downhill slide into overreaching and overtraining, accumulations of microtrauma. And again, this becomes a metabolic phenomenon where it's these catabolic signals, right? We're just degrading and degrading and degrading, and we are not the anabolism, the metabolism that preserves the tissue is not there, so it can't handle in the future after a long period of micro trauma and inappropriate loading. That tendon will not be able to handle the same deformation, the same amount of a load and deformation stretch. It won't be able to handle. Now, usually musculoskeletal injuries, the most common thing you're going to see here is the muscle tendon junction, the myotendinous junction, muscle tendon junction. And there's a lot of reasons for why this area seems, especially distal. You're going to have two of these things, unless it's a fleshy attachment, where you don't have a tendinous attachment. If it's intercostals or something like that, those attached to the rib, but okay, whatever. But in muscles that have your classic muscles that you think of, this fibrous attachment where you have this tendon, you're going to have a myotendinous junction at both ends, right? At the proximal and distal end. And it tends to be the distal end where you see a lot of these injuries, these ruptures, these tears, these strains. It's happening usually at the distal myotendinous junction, and maybe a failure of the integrin fibronectin interface. You know what integrins are. But maybe the sarcomeres here, they're a little bit less distensible. And this just tends to be a vulnerable point, sort of the weakest point. You go from bone to tendon attachment, to tendon, to myotendinous junction, to muscle belly, to myotendinous junction, to tendon, to tendinous attachment, to bone. And the weakest link in that chain tends to be the myotendinous junction. And often what you're seeing is the distal end. You're seeing the farther away end where you're getting that rupture. Now, remember this course of healing, where you get a rupture, you get a tear, your muscle does something wrong, and you ouch, you grab it, you rub it, you say, call 911, even though you just pulled your hammy, but you're overreacting, and your body's normal reaction, your body probably won't overreact. Your body's normal reaction, again, let's vasoconstrict for a minute, because we can't just leak unless you have hemophilia, and that's bad. Nobody with hemophilia loves blood, right? Heme and philia, we love blood, right? That's not what people with hemophilia are so scared of blood, because that's death. That's the reaper, right? Swinging its very fluid scythe at their whatever tissue, and but hemophilia, you're just going to leak. But for people who are able to clot, if you clot, you plug it up, you vasoconstrict, clot, plug it up, and then you become leaky. Because remember, you need to get your cells, all these immune cells are going to show up. You need to get those cells out of the blood. Let's say it's your hamstring, it's a hammy, and semitendinosis or membranosis or whatever, the biceps one, it's some hammy muscle. It's the distal myotendinous junction. That does not live in your blood supply, right? It's not completely surrounded by vasculature. It's not encapsulated by blood vessels. It's not in here, right? It's out here. The torn muscle is outside, not inside. So what you have to do is get leaky. You have to get leaky, and lots of stuff, I highlighted it in red, lots of stuff is going to contribute to the leakiness. That leakiness is going to arise from a number of things. And this is just a closer look. We don't need to go into this with any amount of detail, but a closer look at how the leakiness works, how stuff gets across. It's a great article, this one is. And this is all of these mediators, right? What's a cellular source of these things? What's the mediator? And vascular permeability? What happens to the vasculature? Does it become more permeable? Does it become less permeable? And so how that stuff works. And then once it becomes permeable, then you send all of these immune cells into the area because it's a mess. It's a mess in there. You have to clean it up. And neutrophils, that's frontline. That's Rambo. That's like Sylvester Stallone with lots of guns going in and just shooting shit up. And just like mass execution. I mean, it's Sylvester Stallone against an army, and he's just in there just blasting away, just shoot anybody there. That is your neutrophils, the first responders of the immune system. Okay, platelets, fine. Resident macrophages, fine, whatever. There's some cells, but the cells that go in and like kill stuff, let's go find bacteria and slaughter the bacteria, right? That is going to be the neutrophils. That's the front line sort of military that goes in there with guns. And if they don't, fulfill their task in short time, they just start, shooting up anyway, and then they die, right? So if you've ever popped a zit, and you squirt that like gross pussy stuff all over the mirror, stuff, that's a bunch of neutrophils. That's a bunch of neutrophils, and if you don't pop the zit, it goes away. Okay, it eventually, right? It's like white and it lives there for a while, and then it just like digests, right? It's gone. It's like, where did it go? Well, the macrophages came in and ate it, right? Okay, you didn't pop it over the mirror, so I got to eat this shit, right? So the macrophages go in there and phagocytic cell, it's a dining cell, macro version of a dining cell. It goes in there and eats that stuff up. But the macrophages huge regulators of the healing response. Macrophages really regulate the healing response, to the point where the salamander, you know how you pull off a tail on a salamander and those things grow back? It has like limb regeneration, like it's running away and just leaves his tail behind, and his tail continues to like flop around, and so it's a distraction. But I don't know if the salamander, a lot of creatures will do that, like the tail just leaves and then they regrow those things. We'll block macrophages, and guess what doesn't regrow? I mean, it's mean. It's like, fuck, I'm supposed to get a tail back. Now I'm missing. Now, like, I have like a pirate stub. Like, I'm going to have a little wooden peg for a tail now because, in like a little tiny thing of rum or something. And so macrophages required for that. So don't think of macrophages as exclusively eating zits. Macrophages, yeah, they go in and eat up everything, but they also send out these chemotactic signals, especially when they make their exodus from a wound site after they clean up this wound site and eat it all up and put it all in garbage bags to haul it to the dump. After they've done all of this, they send out signals for the fibroblasts to come in. So they sort of make their exodus and summon all these fibroblasts that are going to come in and start laying down all that collagen, right? You got to heal. You're going to produce a bunch of protein, a bunch of collagen in the area. Now, collagen, you have to produce this stuff right. You have to produce your collagen right. And at first, you're producing a bunch of collagen 3. A bunch of collagen 3 comes in there first, and that doesn't look good. I mean, it looks fine if that's, I don't know, like brain matter maybe, or something like that, or like, a pasta feed or whatever. I don't know. But collagen 1, see these thick, long bands, these beams, these support beams of collagen 1, that's what you want. And remember earlier I said 70 to 80% dry weight of a tendon, you're going to have a bunch of collagen 1 in there. Now, collagen 3, that's what comes first in an injury. You start laying down a bunch of collagen 3, necessary for healing. And you're going to gradually break it down with these collagen ACEs enzymes. You're going to be breaking this stuff down and replacing it with collagen 1. So there's a metabolism here. There's a catabolism and an anabolism. but you got to get it right. If you get it wrong, you can see wrong. You just look around you, maybe even look on your own body. Do you have a bunch of like keloid scarring, like these clumps of scarring? Hey, collagen got a little bit out of hand, right? There's a lot of collagen in there. You're a collagen hoarder in that particular region if you have that kind of scarring. If you have stretch marks, maybe you're a little bit shy on collagen in that area, right? You're living simply or something. You had a estate sale of your collagen, something. So you want to have nice regulation in all of this. And sort of the theme of this class, the theme of the semester is regulation in response to stress. Injury, the stress got the best of you, and you got to have regulation in the healing environment if you want nice healthy tissue at the end. If you don't want a bunch of scar tissue to develop at the end, now immediately you're going to have some scarring, right? But ideally you're going to have enough regulation to wind up with functional healthy tissue at the end of all of that, matrix reorganization, getting all that collagen in the way that it should be. Now, load profiles. We've been talking about load profiles since like day 3 or something. And with loads, these are signals, these are inputs that our body responds to. So we're going to have a bunch of fibroblasts coming into the area. Remember, a macrophage is going to exit the area. When it exits the area, it's going to call in, there's a little bit of overlap, but it's going to call in the fibroblasts. Now, you need nice mechanical signaling. You need nice chemical environment and mechanical signaling to tell the fibroblasts what to do. If you have inappropriate signaling, chemical and mechanical signaling, inappropriate, it can differentiate incorrectly. So myositis ossificans is the stresses on your body following injury. Now, it could be microtrauma, it could be macrotrauma, but the stresses on your body during this healing stage are inappropriate, and your body differentiates those fibroblasts into osteoblasts. So you get inside of a tissue, inside of a non-bone tissue, and you're looking at bone developing. That's not functional tissue. There's no contractile proteins that's terrible. You don't want that. You're not going to get it. There are people on campus, there are employees. I know of at least one employee on campus who actually has this. He was a baseball player and then became a softball player, and playing beer league softball, he wound up with myositis ossificans. His muscle was becoming bone, right? So there are explanations for how this stuff works. Now, we can take advantage of it medically. What do old people struggle with? Osteoporosis. Old people, they're breaking their hips. You break your hip, and that's terrible, right? Because now you're not moving, you're very inactive, and we know the consequences of a sedentary lifestyle. Those consequences are dire in older people, right? And it's cognitive. The cognitive decline happens in like 3 days. You just start seeing the confusion set in, and they were on Jeopardy a week ago, and now they can barely remember your name. I mean, in elderly populations, if you do not preserve mobility, physical activity, exercise, engagement with your tissues, you lose function in a hurry. Skeletal muscle function and cognitive function, cardiovascular, everything starts to deteriorate. So a broken pelvis is horrible, right? And so a major problem in elderly communities is going to be porous bones, osteoporosis. So how about we get some of these fibroblasts to differentiate into osteoblasts? You can do it. You can totally do it. We've figured out how to do that with a bunch of transcription factors, and it just informs these fibroblasts to differentiate into what you want them to differentiate into. So osteoblasts in this case. And so the reprogramming of these things. Now in skeletal muscle, MyoD. MyoD is a transcription factor. This is a very early marker of myogenesis, muscle genesis, and it is activated in response to exercise stress. MyoD, sort of quiescent, it's sort of napping, and in response to exercise stress, you activate MyoD. And through that, you get a commitment to myoblasts. Now, after injury, after exercise, after tissue disruption, if you sit down and sleep and watch all three Lord of the Rings movies in sequence, the extended versions, that's like a whole day, and that's what you do, you're not stimulating fibroblasts into their myoblast activity. You're not stimulating myogenesis. And so this is one more illustration of the importance of loading, the importance of exercise and chemical and mechanical stresses being applied to a tissue. And this article is talking about what to do in the weight room, right? So go ahead and do X amount of sets of X amount of repetitions at X percentage of your 1RM, and we're going to see some MyoD activity. And who cares about that unless you care about it, whatever. But the different load profiles, the different chemical environments and load profiles, in a word, stress, the different stressors are going to determine the behavior of our cells. In this case, the differentiation of our cells. Do we want good bones or bad bones? Do we want bones in our muscle? Do we want great muscle? What do we want? Well, we respond to the stress profile of all of these things. So again, if you sit in your wheelchair forever and you don't load the tissues, if you put yourself in a cast for eternity, if you lie around and say, woe is me, I sprained my ankle, okay, that thing is never going to heal, or at least it's not going to heal appropriately. You need mechanical signaling. You need mechanical signaling. And if you do it right, if you subject yourself to stresses correctly, you have an injury, you have tissue disruption, whatever it is, you're going to get a sequential response, right? This is that Cellier stuff. This is acute inflammatory, acute immune reaction syndrome or something like that. You can coin a better term than what I just did. But yeah, the platelets show up first. There's going to be some resident macrophages there. And then the platelets come and they degranulate. They come from granulocytes. They degranulate. They release stuff that says over here, over here, over here. Sound the alarm, right? Smoke signals. Everybody, it's over here. That's what platelets do. Neutrophils are the first immune cell to show up and Rambo the site. Let's just squirt superoxide everywhere. You get a skinned knee and there's that like deep brown bottle, and the hydrogen peroxide. You're riding down a steep sidewalk on a skateboard on your tummy as a 7-year-old, and you fall off and skin your knee, and mommy, and she brings out that brown bottle, hydrogen peroxide. So this is what the neutrophils are doing. Superoxide. I mean, squirt some free radicals in there. Let's kill some shit. And then the macrophages come in. They sort of clean up the mess. Macrophages release these chemotactic signals. All right, fibroblasts, you get in here. Let's get some collagen deposited. Let's start putting this back together. Collagen 3 gets deposited first. Collagen 1 comes later. But this gets critical for appropriate loading, appropriate stresses to get optimal integrity of the tissue. You're not going to get good at tissue integrity if you don't have mechanical loading. Let me go for a few more minutes and I'll sort of rush through this thing. I realize we're over. But cells, the nerves are going to notice things. Nerves are going to notice peptides. They're going to depolarize like a pain nerve, a nociceptor. They're going to notice peptides, bradykinin, stuff like that. Right here, you see bradykinins, lipids like prostaglandins. Prostaglandins right there, neurotransmitters. ATP is a neurotransmitter. Acidity, right? Hydrogen ions, the H of a pH, heat, pressure, things like this. Your nerves are going to notice, and you're going to send pain signals. You're going to send ouch information through afferents upstairs to your brain, where you're going to perceive information about owie, 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 it stings, it burns, it hurts, it's pressure, it's acidic, I got punched, whatever it is, it's ouch, right? Now, the problem is nerves are not very well, they're often regulation gets a little bit out of hand, and substance P and a thing called calcitonin gene related peptide, CGRP and substance P, these two things are what's called neurogenic inflammation, nerve generated inflammation, neurogenic inflammation. And this can get a little bit out of hand. What these do, the nerve itself releases these things. Substance P is particularly culpable here, and it causes the extravasation of blood in its luggage, right? So it just means stuff leaves the blood. Let's get leaky and have stuff leave the blood. It facilitates an immune response, but the problem is it recruits these immune cells, and that often stimulates more substance P production, which recruits more immune cells and stimulates more substance P. And you get this, what people would call a vicious cycle. And usually it's not that vicious. This is super vicious if it happens. You end up with all this neural problems and pain chronicity, right? Substance P and pain chronicity. Substance P, whatever, substance preparation, substance powder. Once in a while, you see the substance pain, SP. Who cares? Who cares what P stands for? And just like pH, H, hydrogen ions. Okay, fine, whatever. What does the P stand for there? Potency, potential, power. Who cares? It doesn't matter. Calcitonin gene related peptide. That's another one when you're looking at some of these issues. And it's not limited to those two. Substance P, definitely know that one. Calcitonin gene related peptide, yeah, know that one, but just realize there's other stuff too that you don't need to know that's going to contribute to, I got an injury, regulation was fucked up, and now I have pain all the time. I have chronic pain from this. Now, I know this is what I was talking about, that feedback loop, where it gets a little bit out of hand. With substance P, it can get a little bit out of hand with this stuff. Now, it's not just a cell has so many cell surface receptors here. So if we just focus on a few of them, prostaglandins, you see CGRP, there's histamine, prostaglandins again, bradykinins, there's substance P to a neurokinin 1 receptor, ATP, right? That's serotonin right there. But the proton, here's where heat is, and NMDA and AMPA receptors if we're depolarizing stuff, and THC down here, cannabinoid receptors, and there's your opioids and gamma GABA, gamma aminobutyric acid, the it's an inhibitory neurotransmitter. But there's all of these signaling cascades in the body, and we're not really going to talk about signaling this semester. I do that in other classes. I'll refer to it, I'll reference it a little bit now and again, but there's a lot of these things have complex regulatory interactions, and sometimes they interact with each other. So BK, this is not Burger King, that's bradykinins. And bradykinins, they help activate NMDA and AMPA receptors, these down here, NMDA and AMPA receptors. And they also release prostaglandins intracellularly. So you see prostaglandins being released intracellularly, and then they can bind to their receptor. So you can get this autocrine signaling with these things. And so bradykinins, prostaglandins, these interact. A lot of things interact, but what you really need is regulation, and often you don't get it. When you don't get regulation, when regulation goes awry, what happens? You get things like fibromyalgia, pain all the time, and what is the matter with me? I'm exhausted and I'm in pain all the time. Well, let's take a look at a bunch of different studies. Here's 5 different studies. These are the authors of those studies. This isn't like chemical compounds or something. They're looking at the amount of substance P. Here's the control, fibromyalgia patients. Here's the control, fibromyalgia patients. Here's a control, fibromyalgia patient. You get the idea. So we start to see regulation problems in a lot of these chronic issues, chronic illness. And that is not just pain, but I'm still a good athlete. No, you're affecting your motor output. Afferents affect efferents. Afferents, sensory information, gets sent up to the spine and to the brain, but it messes up both the spine and the brain. It messes up voluntary motor action, alpha motor nerves, but it also messes up muscle spindles. You see, muscle spindles, that's spine and back, right? That's gamma motor nerves. That's involuntary motor contraction. And so all of your efferent actions, both alpha and gamma, can get messed up in the presence of pain. What does that look like? I promise just a couple more minutes. What does that look like? Otson DeLuca is one of my favorite studies, this one right here, and it came out a while ago now. I mean, this is almost 20 years old, but it was this foundational study on this principle, where we have conscious, deliberate um, uh, avoidance of motor actions, right? If your back hurts and you're at the drinking fountain, what are you going to do? You're going to do like that thing where you stand with really wide gait, like your feet are 3 feet apart, so you don't have to bend over very far. You're going to deliberately, consciously, actively avoid recruitment of tissues that hurt. If bending over hurts, you're going to pick up your socks with your foot and like try to throw them in the air and catch them or something if your back hurts. Now, if you just try to do it anyway, if it's like, you know what, fuck it, I'm just going to bend over and get the water any way I want, well, you're going to recruit muscles differently in that situation. So there's an unconscious, there is a reflexive and involuntary alteration of recruitment characteristics. You're going to have a delay in activation of the agonist you were hoping to recruit. You're going to have a different muscle group, some other muscle pick up the tab, an inappropriate muscle pick up the tab. You're going to recruit muscle differently. And so in the presence of pain, if you try to use your tissue, it gets used differently. Now, maybe you can return to play and you can pitch and you can do whatever you want, but you're probably not going to be as good if this happens to you. And your risk of re-injury is going to be much higher. So this becomes a problem. When you look at shoulders, anterior instability, infraspinatus and supraspinatus, just look at those two. There's more that you can look at, long head of the biceps, I mean, there's other stuff that you can look at here, but supraspinatus, this is a control, and then anterior shoulder instability, less action, less activity. What are we using a lot of? That infraspinatus, we really take over with that thing. We recruit muscles differently. Go perform the exact same task, and underneath your skin, your sinews behave very differently no matter how you try to work them. So, sort of a summarizing, this is the last slide for today. Everything else is just review. In summary, injury happens. Maybe it's macro trauma, maybe it's micro trauma, maybe it's a combination of the two. We get sort of a general response. From our immune system, all these chemicals and these proteins and the mobilization of all this stuff and the sequence of those things, pretty general, no matter what the injury is. Chronically, it's very different. Healing is very different chronically. Acutely, it's pretty consistent. Or magnitude, right? There's magnitude differences. How much collagen do we need to synthesize? How many neutrophils are showing up, and how long is this going to take? And what is the substance P situation? The neurogenic inflammation. That the magnitude differences, but sequence is pretty much the same. And regulation becomes critical. Right. And then once everything's under control, we need to apply the appropriate stresses, mechanical loads, mostly, that's mostly what we're in control of, is the mechanical loads, to provide the right environment for these transcription factors to elicit the healing response appropriately. And a lot of people get that part wrong. They just lay off it. Oh, I got injured 6 weeks ago. I'm still just laying off it. Well, what are you doing in the meantime? Well, I watched The Office from beginning to end 3 times, and Game of Thrones, because that's the sort of opposite of The Office, I guess. And what I meant was, what are you doing to apply loads to it? Well, nothing, because it's injured, and if I apply a load, it's going to hurt. So people often get this wrong, but think about the stresses and the loads and the applications of these things based on what a tissue expects, what a tissue needs, and that'll be the last sentence that comes out of my mouth. We went over a bit. Do we have some questions? Oh, Genevieve, you have a question. In the example of rotator cuff muscle recruitment due to pain, you mentioned that some muscles are unconsciously more activated than others. How do you reactivate the inactive muscles? Really super good question. And I don't have an answer to that one. I don't have an answer that's good. I have an answer queued up, but I don't have an answer that's real. Now, if you had an answer to this question, you would be queen of, you would at least own a pretty big island. You could, I don't know, some archipelago somewhere would be yours. And you would have so much money if you had a solution to this, because this is the foundation of physical therapy. And how do we restore appropriate neuromuscular recruitment characteristics? How do we restore appropriate muscle performance to athletes, to non-athletes, to old people, to young people, to anybody, to get their daily life back, right? Whatever their daily tasks are, whether that's elite performance or reaching for cereal at the grocery store. Now, if you exercise in the presence of pain, you're going to, Austin DeLuca stuff, you're going to alter the recruitment characteristics. It's going to happen. Voluntary and involuntary, you can see it on an EMG, and maybe you're an exception, but in general, people are going to alter the recruitment characteristics. Now, what used to be the multifidus, some small kind of spinal muscle that's doing a lot of postural stability stuff, you're going to have some more superficial big stuff doing the tasks that the underlying postural things are supposed to do. Inappropriate muscles are let's say you are a server at a restaurant and you get injured or you get sick and you can't go into work. Someone else picks up your shift. Same thing in the body, right? A muscle is injured and somebody else comes in and picks up your shift. Now, 6 weeks go by and you let them just take your shift over and over and over and over and over. 6 weeks go by and they take ownership of it. No, this shit's mine. I do Monday nights or Saturday, let's say Saturday nights, and there's a bunch of money. No, this is mine. I've been doing this for 6 weeks. You're not going to take this away from me. So how do you get your shift back? How do you show up at, hopefully it's not Applebee's, that would be a difficult thing to, so how do you get your Saturday night shift back at a fancy restaurant? I don't know what's in Stockton, but here's what I had queued up. Booze, right? Use alcohol. One thing, you have to get out of pain. You have to get out of pain. If you're currently in pain, you're going to have problems no matter what. Voluntary and involuntary, you're really going to have problems. Now, can you just take a ton of Tylenol and hope your liver hangs on? Yeah, you can do that. But you're still going to be inhibited. You're going to have, because your brain's working fine. You're going to be inhibited. Now, if you booze up a little, and you're totally uninhibited, you can't even walk in a straight line, let alone avoid using a particular muscle group. And so go get drunk and do yoga. Go to Genevieve. Let's all go to your yoga, wasted, right? Nathaniel will supply the booze and Genevieve will supply the yoga. And what we do is we're very uninhibited and we have the analgesic effect. We're out of pain and we are not inhibited by sort of conscious avoidance. And we get a little bit more loose, a little bit more relaxed, a little bit more willing to move through ranges of motion and recruit muscles that we would otherwise leave dormant. Maybe that multifidus, like, all right, let me give it a shot. This sounds fun. Maybe that's what your multifidus says, is it joins the cause. And so that would be my proposition. I don't know the answer, though. There's probably something that's a little bit more wholesome than that, but I do think that would work. Should anything that elicits any pain whatsoever be avoided during rehabilitation of an injury, then, to avoid undesirable muscle compensation? Probably. Yeah, probably. It depends on the degree of pain. If you're just sore, like you have delayed onset muscle soreness, like, I did squats a couple days ago, and whew, it took me 3 minutes to get off the toilet seat. I just wanted to sit there all day. I just didn't have anything to do. I got bored, so I had to endure the pain of getting up off the toilet. Okay, well, maybe wait another day, but before you can get back on the tennis court and start swinging the racket. But you don't need to be like fully healed and healthy and everything when you get back. Now, beyond delayed onset muscle soreness, let's say it's a return to play protocol. Let's say you get injured. It's your knee, it's your ankle, it's your back, it's your shoulder. You get injured somehow. What's the testing battery to say you are ready to get back on the field? Let's say it's an ankle. You're ready to get back on the field. Now, I think Ricky will be an expert here and will have better commentary than I have. So Ricky, chime in if you have some commentary to add. But there might be a balance thing for the ankle. There might be a balance thing. There's probably going to be a pain thing, a flexibility. Let's see how flexible this joint is. You have appropriate flexibility, and there's balance and maybe some sort of functional test with the ankle. And there might be a strength thing, a calf raise, or some sort of dorsiflexion or something with the ankle. Ready to go. Ricky, correct me if there's some additional testing that's done. Now, what they're not doing, what I've never seen somebody do, is EMG to see if, okay, now, did we restore recruitment characteristics before you're ready to return? Do we have the appropriate muscles contributing in the way that they should, in the timing sequence they should? Ricky, you rehabilitate people all the time.
Yeah, no, I mean, you pretty much hit all the main points. I always tell my athletes, you never really want to push past pain and like rehab, because again, that's going to just aggravate it more and cause more issues, swelling, all that stuff. So it is finding the balance, but you also have to know your athletes and kind of know if they're kind of softer, then, they're going to think like a stub toe is like the worst pain they've ever felt in their lives. So knowing your athletes and then, kind of knowing the limits and all that, but you pretty much hit the main points.
Okay. I really like that point of knowing your athletes. Now, some of the malingerers, and you're going to have people who just, as you said, it's the stub toe. And like, well, that's not, just run it on. Like, why did you even mention that to me? That's nothing. And so you're going to have some athletes who are going to be like that, and getting to know the personalities, getting to know the limitations. But if somebody has a stub toe and they're like totally changing the way they run, like, okay, we're going to start wiring in shit weird. Well, just sit on the bench for this game, Yeah, go play Candy Crush for a while and get to level 200 or something, and then we'll get you back on the field. And so I think that's going to be a huge component, is knowing the athletes and their limitations. And because some athletes are going to need to get back on the field on day one. Like, I gotta get back. It's the Michael Jordans of the world. Like, yeah, but you're actually missing a leg. Like, we need to stitch that leg back on. We could save your leg if we do the surgery now. No, it's the finals. And so some athletes are gonna rush themselves against the advice of medical practitioners, and other athletes are going to use it as an excuse for sort of prolonged sedentary behavior. And finding something in the middle is probably going to be ideal. Yeah, you will alter your recruitment characteristics if you are. And also think about the pain by itself. Are you out of pain? Yes. That doesn't mean that the fibroblasts have done their duty. You're not filled with collagen 1 when you're out of pain. What happens when you're out of pain? Well, a lot of the inflammatory stuff is left, right? You're no longer like depolarizing all those nociceptors. Okay, the inflammation is gone. That just means, okay, once the exodus of macrophages, all those things leave, they call them the fibroblasts, whatever. At this point, you probably don't feel any pain. and you have a torn up tissue. It is not healed, and there's no pain, right? Because you have eliminated all that inflammation. You don't heal. You don't deposit a bunch of proteins at the same time you're degrading stuff. You don't go in there with your immune cells and start like Rambo shooting it up, right? Shooting up all your stuff. You don't do that at the same time you're making all these collagens and trying to reassemble the structure. That would be stupid, right? You don't come in with a wrecking ball at the same time you're building the new edifice, right? You tear up the old one, get all that out of there, and then you deposit the new one. Is there some overlap? Yeah, there is a little bit of overlap. Is there a lot of overlap? No. And so once the wrecking ball has come through, the immunological wrecking ball has done its deed, and you've sort of trashed it and cleaned up the trash and gotten it all out of there. Now we get this influx of fibroblasts and we're depositing all this tissue. It's going to be a while before the tissue has good integrity. So the break point, let's say this is a healthy break point of the tissue. This is uninjured before injury, right? And now you injure yourself and your break point is down here, right? I'm trying to angle it correctly. Your break point is down here. And like it's starting to get better. It's starting to get better. It's starting to get better. You have no pain at all. Like, okay, maybe give it a little bit more. Let's get up here so you don't go for your first kick on the soccer field and you crumple down and somebody's there with their iPhone and whatever. Let's give it a little bit more time. And I think people err on the side, kind of like my rant a few lectures ago, where I'm just like, man, college athletics in particular, we're just like, get everyone on the field now, overtrain everybody. Let's just make sure everybody is destroyed for adulthood. That sort of, I think with injuries, we drive people to injuries with excesses of load, allostatic. I mean, it's just pouring on the athletes with all these loads, emotional and social and scholastic and physical loads. We drive people to this elevated injury rate. They get injured, and then we shove them back in when their break point is here. Like, well, okay, the fibroblasts are still in there doing their thing. So I think there's a lot to talk about, and I don't necessarily have solutions to any of this. I'm the one who said go get wasted and do yoga, so I don't necessarily have optimal solutions. But if you can come up with a good solution, a well-reasoned, physiologically, biomechanically, stress physiologically sound reason, I mean, you're going to be like an emperor. You basically said it's okay for me to be wasted for my next lift. Yep. Just get one of those water bottles that it's like metallic and you can't see what's in it. And
can you hear me? Can you hear? Okay,
yeah.
I'm in the middle of practice, so there's like basketballs bouncing around behind me. But I currently am dealing with an inactive shoulder on the left side. Like some muscle is not working right, so there's like weird overcompensation of my trap on one side, and it takes me like physical effort to think about using my lat on my left side. And so there's the buzzer.
That was that was an intense buzzer.
It is. It scares the shit out of me all the time. But the graph that you showed where there's like overcompensation for muscles when like one muscle is damaged, I was like, yo, that's my left shoulder right now. So that's why I was wondering.
We have an EMG. We could hook you up to it and take a look at what your shoulder is doing.
Brilliant. I'm in.
Okay. And 16 lead EMG or something like that. Just throw it on there and just bilateral comparison. See what your shoulder's doing. What is this one doing? What's this one doing? And you could come up with therapeutic. You don't just have to be like RUM and external rotation, but you could come up with exercises that might target the muscles you're hoping to work. I mean, you could do it sober, but if there's pain involved, it's helpful to get out of pain before you do it. Have you ever had an injury and then you just think about the injury all the time? It just never leaves your head, and so the sensation lingers longer than it should because you assign thought to it. You just have this constant conscious relationship with the injury. It's a knee or something. I was just thinking about it, and And so if you're distracted, you don't feel it. You get like super distracted, you're having a great time, you don't notice. And then you go home and you lie down in bed at night and there's no distraction at all. And like, oh, my injury, and so sometimes we just need a life of distraction in order to restore ideal or something close to proper function. The brain can be an opponent sometimes, and I'm as culpable as anyone with having consciousness sometimes side with the opposing team. Okay, it's like getting late on a Friday. Should we call it?
I just had a question about comps.
Yeah, so I did see your email. I haven't responded yet. I've been meaning to respond. It's going to be great, and I think you have nothing to worry about. I haven't read your outline yet. I saw you sent me the outline.
Yeah, I sent you one for 248 and 279 just today. So I mean, if you have a chance, I just want to get some feedback. But yeah, I just wanted to see what you thought.
I also have 100% faith in you. So move forward with faith, but I will also take a look at it, and if I have some suggestions that wouldn't be a hassle, what I don't want to do is start over and do whatever, but because you're going to be fine. Like I know the quality of your work. It's fantastic. I trust there's like, 99.999% trust in the quality of your work. Maybe 1 out of every 10 or 100,000 occurrences, like, you could have done a better job. I know the quality of your work. It's really good. So that said, if there's some little nudge that I can say, oh, consider this or something like that, I'll send you that.
Awesome. Yeah, thank you. I really appreciate that.
Yeah. All right.
Have a good weekend. I'll talk to you soon.
All right, you too.